This video is for lesson 7 of the GCSE Waves topic entitled Refraction. By the end of the lesson you should be able to recall what happens to light when it travels from one transparent material or medium to another, explain how refraction occurs, be able to draw the path of light when it travels into more or less dense transparent materials, and recall that different materials refract light by different amounts. Straight into some note taking then. Could you put the title Refraction, and you need at least a copy of the text that I'm going to talk through now. When light travels from one transparent material, sometimes called a medium, into another, e.g. from water into air, it is caused to change direction, and this changing of direction is what we call refraction. Refraction occurs because light travels faster in some materials or mediums than in others. For example, light travels faster in air than it does in water. Okay, so let's look at what happens when light travels from air, a less dense material, a less dense optical material, into glass, a more dense optical material. Okay, so on the left hand side, the beam of light, or ray of light, is going to travel and hit the block at that point there. Now when it does, the beam of light slows down. In air it travels at around about 300 million meters per second. It slows down to about 2/3 of that when it enters the glass, to around about 200 million meters per second. Now once that beam is in the glass, it travels in a straight line until it gets to the point where it's about to leave. Now when it's about to leave, it's leaving this more dense area of glass into the less optically dense area of air, and it's caused to speed up again. So refraction only occurs at these boundary points here where it's changing speed. Now the question is, why does it change direction? It's easy to see why it changes speed because of the difference in densities, but why does it change direction? We can use a little model to help us explain why we get this bending or changing direction of the light. If we think of a car travelling along a tarmac road as being equivalent to the light travelling through air, and the car travelling through a muddy patch as being light travelling through glass or water, then we can explain why we get this bending effect. So to begin with then, the light or car is heading towards the optically more dense material or mud here. Now at the point at where it's just about to enter, can you see that this wheel here enters the mud first? So this wheel is going to slow down. That will carry on at the same speed, however, so the whole vehicle will be shifted in a sort of clockwise direction. Okay. Now you can think about this if you've ever been in a rowing boat and somebody's rowing harder on one side than the other. The boat will pull in the direction of the person who's pulling hardest. It's the same thing going on here. Now, once all four wheels are in that mud, the car will then continue to travel in a straight line as light does in glass. It'll be at a slower speed. If it's glass, it'll be about 2/3 of what the speed is in air. If it's mud, who knows, but it'll be slower. So if we continue that, then you can see that when it comes out, this wheel here, the opposite wheel, comes out first, and so it speeds up, causing the car to move in an anti-clockwise direction. So it rotates it again, but in the opposite direction. And that's why we get this change in direction, because one part of the light beam, or car in this case, enters or leaves the more optically dense material or mud sooner than the other part. Right, you need to be able to reproduce the diagrams that I'm going to show you later on, possibly in an exam, so you can make sure that you've got plenty of space to draw these and you can annotate around them. Okay, so we're going to look first of all at the example of the ray entering at an angle. We've drawn in our normal line, which is at right angles to the surface, where the ray hits the block in this case. It could be glass, it could be plastic. When it does, as we've seen, it will be caused to bend or refract. Now this angle here between the incident ray and the normal is the angle of incidence. This angle here between the refracted ray and the normal is called the angle of refraction. Now that's what happens when it comes in and slows down. when it comes out again, it's caused to refract in the opposite direction. Now when you're drawing this in an exam, make sure that that line there is parallel to that one there. You'll get marks for the direction in which you've drawn it changing, but you'll also get marks for these being parallel. Okay, there's a second diagram here to show you what happens when light travels down the normal line when it hits the block head on. What do you think might happen here? Well, it's fairly straightforward. The ray of light just carries on as it would do normally, as if the glass wasn't there. It does, however, slow down, but there is no change in direction because all parts of the wave actually enter the glass and leave the glass at the same time. So there's no rotation at all. So just be aware of that. It's a sort of special case. There is no bending when the light travels down the normal line. Okay, pause the video, make sure you get a nice clear diagram of what's on the screen there. Here's something you can try at home. If you take a cup and place a coin in that cup, stick it down with a little blue tack maybe, and then move yourself backwards so you just can't see the coin. Make a note of where you stood, where you just can't see it. Add some water, and you should be able to see that when you do that, you can actually move a greater distance back and still see the coin, and that's because of this refraction effect. Okay, the coin also appears to be higher up in the water because your eye again is tricked into thinking that light always travels in a straight line. It's important to realise that it's not only light waves that can be refracted, all waves can be refracted, and sometimes on an exam paper they'll ask you to talk about the refraction of water waves. So this needs to be in your notes. So when water waves travel from a deep to a shallow region, they are caused to slow down, just like when light enters glass. So light travels more slowly in a shallow region. As a result, the waves bunch together and their wavelengths get shorter. The frequency of the waves, however, remain the same. So wavelength gets smaller, frequency stays the same. When light enters glass, its speed decreases, its wavelength decreases, but its frequency, its colour remains the same. Okay. Now, again, tricky diagram to draw, but it is one that you could be asked to do that. So can you make sure, please, that you draw this as accurately as you can, making sure that the wavelengths that you've drawn here in the shallow water are shorter than those in the deep water. Pause the video now and again try and make sure that you get this diagram as accurate as you can. Right, now what I'd like to do is to complete the short Seneca exercise that's been set for you on waves at a boundary. So it'll assess some of the work that we've done today on refraction and in the previous lesson on reflection. Could you please check on Show My Homework for the appropriate class, and hence you'll get the correct work sent through to you. Okay, so finally then, you should now know that when light travels from one transparent material or medium to another, it's caused to bend or refract. Refraction occurs because light is caused to slow down when it enters a more optically dense material and speed up when it enters a less optically dense material. That when light enters a more dense material, e.g. glass, it bends towards the normal. When it enters a less dense material, e.g. air, it bends away from the normal. Different materials refract light by different amounts. For example, most glass will refract light more than water. And when waves are slowed down, their wavelength gets smaller, but their frequency remains the same.